Our next topic is buffers, and we're going to be looking at the definition of a buffer, the various types of buffer, and the all-important calculations. So diving straight in with the buffer definition, these are solutions that resist changes in pH when small amounts of acid or base are added. So here we are monitoring the pH changes of a buffer solution when we add a strong base such as sodium hydroxide. Now these flatter horizontal regions of the titration curve represent the buffer regions. And here you can see as you increase the volume of your strong base, there's only a very small change of pH, so it's acting perfectly well as a buffer. Now if you neutralize half a weak acid, you end up with a buffer whose pH is equal to the pKa of the acid, and the reason for that is because it has an equal supply of HA and the A- ions, which remember we call the half neutralization point. So there are two types of buffer. One is an acidic buffer and the second type is a basic buffer. I'm now going to talk you through how acidic and basic buffers work. Remember, always bear in mind that you're trying to resist changes in pH when you add an acid or an alkali. So starting with acidic buffers, they're made from a weak acid, remember this partially dissociates, and a soluble salt of that acid. And if you think about it, it makes sense because the weak acid will react with any base you add, and the soluble salt will react with any acid you add. So here's your general equation. Your weak acid sets up in an equilibrium where it releases H+ ions and A- ions. The acidic buffer will maintain a pH of below 7. So how can we go about making an acidic buffer? Well, as I said, we need a weak acid. In this case, we've added excess ethanoic acid to a strong base, potassium hydroxide, and that allows our ethanoate ions to be produced. And we mix those with a solution of ethanoic acid to create the buffer equilibrium, where you have ethanoic acid dissociating to form H+ ions and the ethanoate ion. So in the case when you add alkali to your solution, how do we resist a massive increase in pH? Well, those alkali ions which have been added react with your weak acid in your buffer. So in this case, it would be the ethanoic acid. Here's your general formula of a weak acid in this case. It's going to produce water in a neutralization reaction and A- ions. And by doing this, the hydroxide ions are removed and the pH remains almost the same. What about when you add acid? How do we prevent a massive decrease in pH? Well, as you'd expect, your acid donates H+ ions, and this reacts with your soluble salt ions, which are present in your buffer. So in the case here, it would be the ethanoate ions. By doing that, it moves the position of equilibrium to the left, increasing the amount of, in this case, ethanoic acid. Your ethanoate ions here would decrease, meaning that the pH remains almost the same. And now let's consider how basic buffers work. Well, in this case, they're made from a weak base, something like ammonia, and a soluble salt of that base. They work by maintaining a pH of above 7. So here we have our weak base, the ammonia solution. We mix it with the soluble salt of that base, so in this case it's ammonium chloride. The ammonia solution partially dissociates, producing an ammonium ion, hydroxide ions. The salt we've added fully dissociates. So what happens when alkali is added? How do we prevent a massive increase in pH? Well, the hydroxide ions present in the alkali react with the ammonium ions present in the buffer. By doing that, it removes some of the hydroxide ions. And according to this reaction, it means that more ammonia forms, meaning that the pH remains almost the same. What about when we add acid? How do we prevent a massive decrease in pH? So what happens here is the H+ donated from our acid reacts with hydroxide ions. The hydroxide ions up here, the buffer equilibrium moves to the right, more ammonium ions form and the pH remains roughly the same. And obviously remember your equilibrium chemistry, by decreasing hydroxide ions, it will automatically move the position of equilibrium to the right in order to increase their number. How to calculate the pH of an acidic buffer solution. The acid dissociation constant Ka for weak acid has a value of 1.35 times 10 to the minus 5. A buffer solution was prepared by dissolving 0.0236 mol of a salt NaA in 50 centimeters cubed of 0.428 mol per dm cubed solution of weak acid. Calculate the pH of this buffer solution. So as we know, we have an acidic buffer solution. So the way in which we're going to do this is we're going to calculate the concentration of the salt formed. We're going to write an expression for Ka, so our acid dissociation constant. We'll use that to calculate the concentration of H plus ions, and then it's the simple expedient of subbing in our concentration of H plus ions into our pH equation that we're very familiar with. In step 1, we're finding the concentration of our salt, NaA. So concentration, remember, is number of moles divided by volume. We know the number of moles is 0.0236. The volume we were told was 50 centimeters cubed. Do divide that by 1,000 to get it into decimeters cubed. Our concentration is 0.472. Next step is to write an expression for Ka. Remember, our equation for the dissociation of our weak acid looks like this, which is why this is our expression for Ka. It's our concentration of products multiplied together divided by our concentration of acid. Ka, they told us, was 1.35 times 10 to the minus 5. One thing to be a little bit careful of is you need to remember the fact that because our salt is going to completely dissociate, it means that we can infer that our concentration of A- ions is the same as our salt concentration. Concentration of acid we were given in the question. So our concentration of H plus ions equals 1.22 times 10 to the minus 5. So finally we can find pH. So our final pH is 4.91. So to recap, we found the concentration of our salt. We then wrote our expression for Ka. Because that salt completely dissociates, it means that our concentration of A- was exactly the same. Now, one thing I do want to point out is you cannot write this formula here, which you will have seen previously. And the reason for that is because the concentration of H plus ions by definition does not equal the concentration of A- ions in a buffer solution. And then by solving to find our concentration of H plus ions, it enabled us to find the pH. Now we're being asked to calculate the pH of a buffer solution with equal acid and salt concentrations. So a buffer consists of 0.1 mole per dm cubed ethanoic acid, 0.1 mole per dm cubed sodium ethanoate. What is the pH of the buffer? And Ka for ethanoic acid is this. Now, by definition, when you have equal acid and salt concentrations, we've reached our half neutralization point. So to remind you, it's this portion of the graph here where you've added half your volume in order to neutralize either your acid or your alkali. And so we can make this statement, which is at that half neutralization point, the concentration of H plus ions equals the concentration of A- ions, and therefore that pH equals pKa. So now we can calculate pKa of the acid. So pKa is minus log to the base 10 Ka. Building on everything we've learnt previously, we said that because pH equals pKa, we know that the pH is therefore 4.77. Remember, these three dots mean because, these three dots mean therefore. Calculating the mass of salt required to make a buffer solution. A buffer solution is made using benzene carboxylic acid and sodium benzene carboxylate. According to this equation, calculate the mass of sodium benzene carboxylate with an MR of 144 that should be dissolved in 25 centimeters cubed of 0.1 mole per dm cubed solution of benzene carboxylic acid to produce a buffer solution with pH of 4.05. The pKa for benzene carboxylic acid is 4.298 Kelvin. Assume that the volume of solution remains constant. So lots of different terms here that you'll have come across. I know it's all about making sure that you do everything in the right order, but if you're not sure, you can definitely find, if you've got pKa, that will enable you to calculate Ka. You'll be able to write an expression for Ka. Hopefully you'll be able to work out H plus ion concentration. So it's somewhere to get started. Now, in terms of how we're actually going to go about answering this particular question, our first step is to indeed calculate the value of Ka, so the acid dissociation constant. for our weak acid, our benzene carboxylic acid. So Ka, remember, is given by 10 to the minus pKa. Step 2, we're going to calculate the concentration of H plus ions using the pH of the buffer solution. So our concentration of H plus ions is 8.91 times 10 to the minus 5. Step 3, we're going to find the concentration of the benzene carboxylate. And in order to do that, we need to write an expression for Ka. So Ka equals concentration of C6H5COO minus multiplied by a concentration of H plus ions divided by the concentration of our acid. So Ka we just found to be 6.31 times 10 to the minus 5. We're after our concentration of benzene carboxylate. We just found our concentration of hydrogen ions. And then finally the concentration of the acid was 0.1. Once you've rearranged, our concentration of benzene carboxylate ions is 0.071. We're so close now because we're being asked to find overall the mass of sodium benzene carboxylate. We have the concentration, which means we can now find the number of moles. Which we do by doing the concentration times volume. The concentration we just found, the volume was 25 centimeters cubed. Get that into decimeters cubed. And then final step, find the mass of C6H5COO minus. We do number of moles times MR. They told us that the MR was 144. So our final answer is a mass of 0.25 grams. To summarize, to find the mass of salt required to make a buffer solution, we used all the information in the question to calculate Ka by doing 10 to the minus pKa provided in the question. We found the concentration of H plus ions, very similar maths, 10 to the minus pH provided in the question. Then we wrote an expression for Ka, substituting all the values either just calculated or given in the question. That enabled us to find the concentration of benzene carboxylate ions. We then used that to find the number of moles, and then finally we found the mass by doing number of moles multiplied by the MR. One thing I should mention is that dilution with a small volume of water does not affect the pH of a buffer solution, and that's because the ratio of the A- ions, so for example the ethanoate ions, to the concentration of the acid, for example the ethanoic acid, remains constant, and then due to this equation here, the concentration of H plus also remains constant. Time for another calculation. So this time we're calculating the change of pH when adding a base to an acidic buffer solution. So remember, an acidic buffer solution will contain a weak acid and a salt of that acid. So in this case, a buffer solution was prepared by adding 0.0142 moles of potassium propanoate to 100 centimeters cubed of 0.5 mole per dm cubed solution of propanoic acid, mixing thoroughly. 2.5 times 10 to the minus 4 moles of potassium hydroxide was then added. Calculate the pH of the buffer solution after adding that potassium hydroxide. And for propanoic acid, the value of Ka is this. So the way in which we're going to go about this question is we're going to write an expression for Ka for the buffer solution. We'll find the initial number of moles of propanoic acid. We can see here that we have volume and concentrations. That should be very straightforward. We're then going to calculate the amount of propanoic acid remaining after the addition of our strong base, the potassium hydroxide. And this will enable us to find the number of moles of propanoate ions and then various concentrations, so that we can rearrange to find the concentration of H plus ions and finally calculate pH I know it sounds super complicated, but the order is logical. So we'll start by going through step 1. We'll write an expression for Ka. Let me just write the equation. So here's your propanoic acid. So weak acid, it dissociates partially into our all-important H plus ions and our propanoate ions. So we can see straight away that our expression for Ka looks like this. Our next step is to find the number of moles of propanoic acid, so our weak acid initially. So it's concentration times volume. Concentration was 0.5, volume was 100 centimeters cubed. So our initial number of moles of propanoic acid was 0.05 moles. Now we need to find the number of moles of propanoic acid remaining after the addition of our strong base. So I've just underlined the two key number of moles here. So number of moles remaining will be our starting moles minus the number of moles of potassium hydroxide. So we have 0.0498 moles of propanoic acid remaining. Now we need to find the number of moles of propanoic ions in solution. I'm going to change colour of highlighter for you to see this more clearly. So what will the number of moles of propanoate ions in solution be? Well, it will be the number of moles we started off with plus the number of moles of potassium hydroxide. And that's because the hydroxide ions present in that potassium hydroxide react with the propanoic acid to give water and the propanoate ions. We're getting closer now. We're almost ready to sub in numbers for our expression for Ka. The first thing we want to do is find the concentration of propanoate ions and find the concentration of propanoic acid. Our volume up here is 100 centimeters cubed. So there's our concentration of propanoate ions. What about our concentration of propanoic acid? And now we're on our home stretch. We're subbing our values into the expression we wrote for Ka, and therefore we're finding the concentration of H plus ions in the process. So we're going to steal this expression. Ka equaled 1.35 times 10 to the minus 5. Concentration of H plus ions is what we're after, and we just found out the other two values. And step 8, we're going to calculate the pH. So wow, that was certainly a very complicated question. So what were we doing? We were finding the change in pH when we add a base to an acidic buffer solution. So our first step was to write the expression for Ka. We then calculated the number of moles present in solution of the propanoic acid by doing concentration times volume. So we used these two numbers here to find that we started with 0.05 moles of acid. Then we needed to work out how much reacted, so how much was left over. So we took that number that we started with initially and then minused, in effect, the number of moles of potassium hydroxide, because the hydroxide ions, after all, react with the propanoic acid to give water and propanoate ions. So that was the number of moles of acid remaining. Then in order to find the number of moles of propanoate ions present in solution, we took the initial number they told us and added the 2.5 times 10 to the minus 4, because remember, when a base is added to an acidic buffer, the amount of weak acid decreases. And that's because when we add our base, what happens is the amount of this decreases, but the amount of the salt increases. So that's why we added that number there. Then we found the concentration of propanoate ions, the concentration of propanoic acid. That gave us enough numbers to substitute into the expression for Ka. We solved to find the concentration of H+ ions and then finally found the pH. So in the previous example, we calculated the change in pH when adding a base to an acidic buffer. This time we're adding an acid to an acidic buffer. In a buffer solution, the concentration of ethanoic acid is this, the concentration of sodium ethanoate is this, Ka has a value of this. Calculate the pH of this buffer solution. So slightly more straightforward. What you want to do first of all is find the concentration of H+ ions in the original buffer solution. So write our expression for Ka. You should be nice and familiar with this by now. So Ka we were told was 1.74 times 10 to the minus 5. We're after the concentration of H+ ions. Solve for H+ ion concentration. And then to find the pH of the original buffer solution, it now gets more complicated if we consider part 2, 10 centimeters cubed of 1 mole per dm cubed. HCl is added to 1000 centimeters cubed of this buffer solution. Find the pH of the new solution. So we will need to find the number of moles of hydrochloric acid added to the buffer. That will enable us to find the amount of ethanoate ions remaining after the addition of HCl. We'll also be able to calculate the amount of ethanoic acid now in solution, and then based on our expression for Ka, we'll be able to find the concentration of H+ ions. So step 1, find the number of moles of HCl added. Our next step is to calculate the amount of ethanoate ions remaining after the addition of HCl. To make it easier for you to understand, I've just written a quick equation demonstrating the buffer. So when the HCl is added, what happens is it reacts with the ethanoate ions, meaning therefore that the amount of the ethanoate ion decreases, forming more ethanoic acid, so that in effect increases. So to pin maths to this, we look back at the wording of the question. We started with 0.1 mole per dm cube concentration. Just look at those units. That means we can infer that we started with 0.1 moles of ethanoate ions. And then we know that the number of ethanoate ions will have decreased by 0.01 moles, because after all, that's the quantity of HCl available to react with the ethanoate ions. So our number of moles of ethanoate ions remaining is 0.09 moles. Our next step is to calculate the amount of ethanoic acid in solution. So through the HCl H+ ions reacting with the ethanoate ions, we know we'll have more ethanoic acid, but how much more? So we have in effect 0.15 moles of ethanoic acid, and then we add the 0.01, which formed when we added the HCl. So we now have more ethanoic acid. We now have 0.16 moles. So I think that's probably the most difficult part of the question done, because we can now find our concentration of H+ ions. One thing to think about here is the fact that obviously the K expression involves concentrations, but if you look at the wording of the question, it says that the volume of buffer solution is 1000 centimeters cubed. So when we say this out loud, we're saying that we have 1 mole per decimeters cubed of hydrochloric acid. So that is in effect 1 mole present in this volume, because 1 decimeters cubed is the same as 1000 centimeters cubed. So in this particular case, we would say we can cancel out the volumes and not worry about them. So our Ka value was 1.74 times 10 to the minus 5. We know we've got 0.09 moles of ethanoate ions, 0.16 moles of ethanoic acid. So we can solve to find our H plus ion concentration, which is 3.09 times 10 to the minus 5 moles present per decimeters cubed. So that's why we can bring those concentration units back in. And then final step is to find the pH. This was extremely nasty, so let's go through quickly what we did again. So in a buffer solution, we know we have a weak acid reacting with a salt of that acid. We have our Ka value. We're being asked to find the pH of the initial buffer solution, which was fairly straightforward as we wrote our expression for Ka, solved to find the concentration of H plus ions, plugged it in to find the original buffer solution's pH. Things got more complicated when we added 10 centimeters cubed of 1 mole per decimeters cubed HCl to 1000 centimeters cubed of this buffer solution. We are asked to find the pH of the new solution. So what we did first of all was find the number of moles of HCl added. And then we had to recall that the way that this particular acidic buffer works is the HCl reacts with the ethanoate ions and therefore decreases the number of ethanoate ions but increases the number of ethanoic acid. So when we calculated the amount of ethanoate remaining, we took the original amount and minus the amount of HCl present in our reaction mixture to find 0.09 moles. We then wanted to find the amount of ethanoic acid, which we knew would be an increase. After all, more ethanoic acid was produced for the reasons I just specified. So we took the original amount of ethanoic acid in the question and we added this value here to get a final total of 0.16. We then subbed in all these numbers to our Ka expression. Remember I said it's okay to not include volumes, and the reason for that is because the volume given was 1000 centimeters cubed, which is in effect 1 decimeter cubed. And then we could solve to find the concentration of H plus ions and finally the pH. At 298 Kelvin, the value of the acid dissociation constant for weak acid is this value. Calculate the value of pKa for the weak acid at this temperature. So pKa is the same as minus log to the base 10 Ka. So to 2 dp as the question specifies, it's 4.52. Write an expression for the acid dissociation constant. So our expression for Ka is the following. Calculate the pH of a 0.17 mole per dm cubed solution of HX at this temperature. Give your answer to 2 dp. So start by getting your acid dissociation constant copied down. Now, one thing you must remember here is that when you calculate the pH of a weak acid, you can assume that the concentration of H plus ions equals the concentration of A minus ions. So these are in effect the same. If you write this statement here, it's fair to say it's the same as the concentration of H plus squared. So that's what we're going to do here, because it makes everything so much easier for us. Remember, this doesn't apply with a buffer. It's only when you're finding the pH of a weak acid by itself. Finally, find the pH. An acidic buffer is formed when 10 centimeters cubed of 0.125 mole per dm cubed aqueous sodium hydroxide are added to 15 centimeters cubed of 0.17 mole per dm cubed aqueous weak acid. The value of Ka is this. calculate the pH of this buffer solution. So we know this is going to be way more involved because it's worth 6 marks. I'm writing this again just so that you can see how we're going to arrive at this answer. Remember how the acidic buffer works is that when you add that strong base, the sodium hydroxide, it reacts with your weak acid to produce these ions here, releasing H+ ions. By doing so, it uses up the acid, it increases the number of negative ions, and that will enable you to find the new concentrations of the acid and the A- ion, and then by using your expression for Ka, you'll be able to calculate your H+ again. So I promise it's not as awful as it sounds. Let's start by writing our expression for Ka. Same old, same old. Let's start by finding the initial moles of our weak acid that's present at the start. So we know we're going to do concentration times volume. The concentration we were told was 0.174. The volume is 15 centimeters cubed. So that's our initial number of moles of our acid. What about our moles of weak acid remaining once the sodium hydroxide has been added? Well, we take our number of moles that we had to begin with. We need to find out the number of moles of sodium hydroxide that were added. So I've done a quick calculation up there. What about the number of moles of the A- ions now present in solution as a result of the reaction between the sodium hydroxide and the weak acid? So the moles of X-, by definition, must be the number of moles of hydroxide ions which were added. So we know that that is 1.25 times 10 to the minus 3. We're so close now. Let's sub in our value for Ka. We're finding our concentration of H+ ions. That equals 3.27 times 10 to the minus 5. So our final answer is 4.49. Buffer solutions are important in biological systems and in industry to maintain almost constant pH values. In the human body, one important buffer system in blood involves the hydrogen carbonate ion and carbonic acid, which is formed when CO2 dissolves in water. Use the following equation to explain how this buffer maintains a constant pH of 7.41, even if a small amount of acid enters the bloodstream. So when that acid enters the bloodstream, it's in effect donating more H+ ions, meaning that the position of equilibrium shifts to the left, and therefore the ratio of the concentration of carbonic acid to hydrogen carbonate ions remains constant, so therefore the concentration of H+ ions and pH remains constant. In a sample of blood with a pH of 7.41, the concentration of hydrogen carbonate ions is 2.5 times 10 to the minus 2. The concentration of carbonic acid is this. Calculate a value for Ka, the acid dissociation constant. Write your expression. Now to find the concentration of H+ ions, remember we do 10 to the minus pH. We were told that was 7.41. And then sub in our values into our expression. In industry, the pH of a solution used to dye cloth must be controlled or else the colour varies. A solution of dye in a beaker is buffered by the presence of ethanoic acid and sodium ethanoate. In this solution, the concentration of ethanoic acid is this, the concentration of sodium ethanoate is this, the value of Ka at 298 Kelvin is this. A 10 centimetre cubed portion of 1 mole per dm cubed HCl is added to 1000 centimetres cubed of the buffered solution. calculate the number of moles of hydrochloric acid added. So number of moles is concentration times volume. Calculate the number of moles of ethanoic acid and the number of moles of sodium ethanoate in the solution after the addition of HCl. Let's start here with the mole of sodium ethanoate after the addition. So you add hydrochloric acid, and what it does is it reacts with the ethanoate ions, in effect using them up. Just look up here, we're told that the concentration of ethanoate ions is 0.1. Because this volume is 1000 centimetres cubed, which is in effect per decimeters cubed, we're allowed to use that as our number of moles to begin with. We're going to minus the 0.01 we just calculated, because after all that's the hydrochloric acid that reacted, which gives us 0.09 moles of sodium ethanoate left over. And then what about the number of moles of ethanoic acid? Well, when the H plus ions from the HCl react with the sodium ethanoate, you're going to make more ethanoic acid. So we'll get our starting number of moles and add 0.01 this time to get 0.16 mole. Hence calculate the pH of the new solution. Final pH is 4.51.